Hello everyone and welcome. Welcome today to our first workshop on the SoFiA project. It will be the first among a series of online workshops, and today's topic will be a connecting bridge, soap films and artificial photosynthesis. We are living in unprecedented times. All around the world, there are major waves of change. And our SoFiA project, we believe, is among one of them, with the potential to change the way how we look at energy, systems, and collaborations. Again, I welcome you, and I will read out the agenda that we have today for you. But before that, I send a prayer for your health and your family's health, and the health and well-being of all your friends and peers. Thank you, and enjoy our presentation. So today's agenda, we have 6 presentations, 6 lectures. I will go through them one by one. The first is this welcome note. Then Professor Leif Hammarström from Uppsala University, who is a world-renowned scientist in artificial photosynthesis and our project coordinator, is going to give an introduction to the SoFiA project and an overview on the artificial photosynthesis and solar fuels. This will be for 20 minutes. Then I personally, my name is Indranil Sen. I will present the project overview and critical aspects of the future and emerging technology grant writing. This is the platform under which our project SoFiA has been funded, so film-based artificial photosynthesis. Then we will have a presentation from a colleague who is not directly involved in the SoFiA project, but he is a peer in the field of artificial photosynthesis, Professor Hai-Ning Tian. It will be based on polymer nanodots for photocatalysis. It will also be 20 minutes. The 5th lecture will be artificial photosynthesis in liposomes from Professor Sylvestre Bonnet from University of Leiden for 20 minutes. And the 6th and the final lecture will be on soap foam analysis using Teclis instruments from Dr. Yusra Timoune from Teclis Scientific in Lyon, France. This will be 20 minutes. And then we will end our today's workshop. Please note that tomorrow we also have a workshop, and it starts the day 2 of the workshop, November 4th, and it will start on 3 p.m. Eastern European time and 2 p.m. Central European time. So we hope you will join us. In case you cannot join us, please note that all of this is of course being live broadcasted, and they will be available later on for viewing because they will all be recorded. Again, this is Indranil Sen, the project manager of SoFiA project, also the director of Wasabi Innovations, a third party that takes care of the dissemination and communication. So I now invite Professor Leif Hammarström from Uppsala University to share his screen and start his presentation. Thank you so much. Leif?
Thank you very much, Dr. Sen. So I will share my screen. There. So thank you very much for the kind introduction.
Sen. So what I will talk about is an overview of artificial photosynthesis and the rationale for the SoFiA project. So my name is Leif Hammarström. I'm at the Department of Chemistry at Uppsala University. I'm also chairman of the Swedish Consortium for Artificial Photosynthesis, who has been working on fundamental research of artificial photosynthesis for over 20 years. So one of the rationales for artificial photosynthesis research is that we want to understand natural photosynthesis. Natural photosynthesis is one of the most important fundamental processes on the planet, and it contains many still unsolved scientific questions and a lot of fundamental research of high interest. If we can also reproduce natural photosynthesis or aspects of that in artificial photosynthesis, this is a way to further understand how the natural photosynthesis and the underlying processes work. But there's also, finally, the interest to utilize artificial photosynthesis for large-scale energy production to reduce our dependence on fossil fuel and mitigate climate effects. And to the left here, you see one of my favorite cartoons on the climate debate here. And there are many reasons to try to stabilize climate change and move over to energy sources that are not fossil. The last years has seen a remarkable increase in renewable energy and not the least solar energy. This is a graph from the Fraunhofer Institute on the total amount of installed photovoltaic capacity in the world. And you see a remarkable growth. This is just 10 years. Since the beginning of this millennium, the market for solar cells has increased by about 40% every year. That is an enormously strong increase for any market. And this is, of course, very positive. What you see here is that while in the middle, around 2010, Germany was very important, and also other parts of Europe in the installations, but more recently, Asia, China, and Japan, for example. But also America has come on very strong and represent a large part of this increase in photovoltaic capacity. International Energy Agency is a very respected agency in the authority on energy information. And this they just in October released their yearly World Energy Outlook, and they say now that solar electricity is now the cheapest electricity in history, and it means that in many countries solar electricity is cheaper than conventional electricity from gas and coal. And this is a remarkable development. And about 10 years ago, I had many colleagues who tried to tell the world that solar photovoltaics will never be able to compete with conventional sources simply because it will be too expensive. And it's remarkable to see that in just 10 years, the picture has changed completely. But electricity is only a part of our consumption. These are data from 2015, but the essential picture hasn't changed much. So less than 1/5, about 1/6 of all the energy we use is used in the form of electricity. Almost 80% of what mankind uses is in the form of fuels. Most of this is fossil fuels. Electricity is a great energy carrier. Electrical motors are extremely efficient compared to internal combustion engines, for example. And electricity consumption is expected to increase its share, but for a long time, probably the foreseeable future, fuels will dominate, and they should rather be renewable fuels. One reason is that fuels are superb for large-scale energy storage. It's important to to recognize the enormous amounts of energy we are using in the world. We're using about 19 terajoules per second. So that's 19 terawatts of power consumption on the average, day and night, all year round. And a typical power station, like oil, doesn't matter if it's oil or coal or nuclear power, that is typically on the scale of 1 gigawatt. So we're using the energy of 20,000 power generating stations working at full maximum capacity all the time. That's the average power consumption we have. And if we want to store a large part of this, we need a huge power storage power, and fuels are orders of magnitudes better in energy density than the best batteries. And we need, which is obvious to see here, especially in my country, in Sweden, it's very obvious to see that we need to store energy between summer and winter, for example. And batteries usually only have a short storage lifetime if they're rechargeable. Natural photosynthesis then is very inefficient. You typically get much less than 1% energy yield. The best energy crops can for a limited time reach 2 to 3% conversion efficiency. And this they do biomass, and photovoltaics are doing electricity, so the products are very different. But if you just compare the energy content, the commercial photovoltaics from silicon, they're giving out about 18% solar power to electrical power. And then biomass conversion, even if it's a different product, in terms of energy conversion, is much less efficient. But the primary steps of natural photosynthesis are efficient. And these are the ones we're interested in mimicking. Photosynthesis is living organisms, and you do a lot of things with the energy except just making biomass. But if we can capture the essence of the primary steps and mimic those principles in smaller man-made systems, we will gain fundamental understanding, but also obtain systems with the potential to be much more efficient than nature in making a solar fuel, a fuel from sunlight, water, and carbon dioxide. And this is what artificial photosynthesis is about. If you're looking at the primary photosynthetic steps, you have to look into the leaves to the left here. You see to the left, you see a cartoon of a chloroplast, a small organelle inside the leaf cells. And there you see stacked membranes. And if you look into one of those membranes, these are lipid membranes, bilayer membranes. This is called the thylakoid membrane of green plants. There you see an array of large protein complexes. And they are able to harvest light. So chlorophylls and other pigments help to harvest light energy. And then they create electronically excited states of the molecules. And these electronically excited states have more energy than the ground state in the dark, and they can do chemistry, photochemistry, that is not available in the dark. They have more energy, so they can drive charge separation reactions where electrons and holes are separated. So an electron is moved to from one side of the membrane to the other side of the membrane. Electrons are fed in by water splitting. So water is split into oxygen, protons, and electrons. And you feed in electrons here, and they migrate through this chain and reach to another photoactive complex, photosystem 1. And they're excited again, and you form the NADPH, which is the hydrogen carrier in biology. So this is used to hydrogenate compounds, for example, carbon dioxide. At the same time, protons are pumped across the membrane, and the protons are used to make ATP, which is an NA carrier, by this complex ATP synthesase. And what you see here are 4 principles. You need to harvest light and funnel this excitation energy to make charge separation, to convert it into chemical energy. But one electron and one hole doesn't do a lot of good chemistry. you need to couple several electrons and holes to catalytic chemistry. And this membrane is a good example of how important it is to have a good organization of your compounds and compartmentalization in a membrane in order to, for example, be able to direct electrons to go in the right direction and don't just recombine with the electrons and holes. And also pumping protons across the membrane. So photocystin 2 is a protein complex that splits water. And here I just look, we have removed all the protein and just look at the redox active cofactors, the electron transfer cofactors. And when the central chlorophylls here in the middle in green, when they are excited by light, they can transfer an electron to the brown pheophytin molecule, as a chlorophyll-like molecule, and then further to quinone A and quinone B. The first steps take a few picoseconds, and then on a time scale of a few hundred microseconds, the electrons are out on the quinone B. And that generates a highly oxidizing chlorophyll radical. And this is able to take electrons from a manganese calcium cluster, the catalyst of the oxygen evolving complex. And here you start coupling the electron transfer to proton transfer, and eventually accumulate several holes here. This catalyst is able to donate several electrons and eventually split water. 2 water molecules form 1 oxygen molecules, 4 protons and 4 electrons are delivered to the chlorophylls by 4 successive photons. So if you're looking essentially here, what you're doing on an energy scale is that you take, this is a bacterial center, but the same principle is in photocystin 2. You excite the central pair of chlorophylls and you separate charge, meaning that you put an electron on this pheophytin and the hole is on the special pair. And in order for the electron and hole not just to recombine, you need to move them further apart. So you're moving the electron further and further away. Every time you take a step down in energy, so you have some driving force for the reaction. So you sacrifice a bit of energy, but the photosynthesis is able to do this charge separation with almost 100% yield, almost completely avoiding the charge recombination reactions that will just waste the energy into heat. That gives you, when you separate the electron and hole on a long time scale, you have the possibility to start doing interesting chemistry. The oxygen evolving complex is a 4 manganese, 1 calcium cluster with oxygen atoms. And it goes through several steps, oxidation steps. The dark stable state is the S1, called the S1 state, but the most reduced state is S0. And today we know the Indra? Sorry. The most reduced state is the S0 state. And every photon that comes into photosystem 2 leads to one step advancement along this cycle. And you see 1 electron is given to the chlorophylls, 1 proton leaves. And you have an alternating path with 1 electron, 1 proton, 1 electron, 1 proton, 1 electron, 1 proton to keep avoiding charge accumulation. And when 4 photons have come, you come to this last transition where oxygen is released and new water molecules are bound. So catalysis is very important in solar fuels. It's a multi-electron and multi-proton reaction. This is true for water oxidation, for proton reduction to hydrogen, or carbon dioxide reduction to a fuel. It could be a syngas or it could be methanol. Still many electrons and many protons. A catalyst in chemistry we usually describe as something that brings down the activation energy between reactant and product. It's true, but this is now not a single step reaction. It's a multi-step reaction. And if you take the free energy accumulated in the reaction versus the number of electrons you add, you see that if you try to take 1 electron, give 1 electron to carbon dioxide, it's a very steep slope. It's very energy costly because this radical is very unstable. If you instead manage to add a catalyst that can take you directly from here to the 2-electron product, the slope is much steeper. And the shallowest slope is the most energy efficient. So if you can make methane with a perfect catalyst, you can go along this dotted line. There are several ways of making direct solar fuel production, which means making a fuel from sunlight, water, and carbon dioxide without going via biomass or electricity. One thing is to use microorganisms that have enzymes to do both water splitting, photosynthetic water splitting, and fuel production. And my colleagues have made butanol with quite good efficiency. You can take molecules that are inspired by photosynthesis, but in completely man-made systems that harvest light, do charge separation and catalysis. You can let semiconductors and materials do the same type of job. Or you can go to very high temperature, 1500, 2000 Celsius, to thermally split water on materials using large mirror parks, heliostats. These two approaches have traditionally been separate, but today they are quite joint, and there are many hybrid approaches where you combine semiconductors and molecules, for example. The first system that showed photochemical water splitting was published in Nature 1972 and was a huge source of inspiration. They just took titanium dioxide, which absorbs UV light. So this system was very inefficient. They had a platinum counter electrode, but they showed that this could be done. They split water into oxygen and hydrogen. This can also be done using semiconductor particles and you can have plastic bag systems. This can also be used with microscopic organisms, that you have very simple engineering plastic bag systems where you collect the different products. The highest efficiency for non-concentrated sunlight is close to 20%. It is from Caltech in California, United States, and they use a multi-layer semiconductor systems this is a lot of engineering of the interfaces to minimize charge recombination. And you can see that 19% is a lot better than what plants do, even if this is only giving electricity. But this is really a Formula One car. These are really expensive materials, and some of the elements are quite scarce. Rhodium, because we need to scale this up to large scale. So this cannot be the ultimate solution. So solar fuel devices is a combination of challenges, and you cannot just brag about one number. You have to simultaneously get a high efficiency, because if the efficiency is too poor, you will need too large areas and too much investment into the system compared to the energy you get out. At the same time, the system needs to be durable. Because if it's very cheap or very simple and self-assembled, that's one thing. But if you really need to manufacture something, you cannot manufacture something that only holds for a day or two. You probably want this to hold for a few years. But the solution must also be scalable, not too economically expensive, but also not use toxic elements and also not scarce elements that will limit the scale up. So today, for example, electrolyzers often use iridium oxide to do the water splitting, and we don't have enough iridium oxide to go to really large scale with such electrolyzers. So there are a lot of fundamental research and engineering needed to reach a system that simultaneously fulfill all these three goals. There are limitations on materials, and for those of you who are interested here, I recommend, for example, this paper from Jaramillo and Noshkov. And basically, the idea is that if you're trying to do water oxidation, for example, that similar holds for CO2 reduction, you have critical intermediates with a certain binding energy to the material. And ideally, to get a highly efficient catalyst with low energy losses, you like to be here. But all materials they try experimentally in the literature and that they do computations for lie along this line, which misses this maximum. So it's impossible to independently tailor the material to get the ideal values of these binding energies. And they discuss that maybe you cannot go for the pure material. Maybe you need to have some molecular structures on these materials to engineer a perfect catalyst. And I think the potential of molecular catalysts is great because we need to control the breaking and formation of bonds between very small molecules, hydrogen, oxygen, carbon dioxide. And if you look at the enzymes, they're very good at doing that. So carbon monoxide dehydrogenase is binding the substrate, carbon dioxide, with multiple interactions with the two metal centers and with several hydrogen bonds to the in 3 dimensions. This is very hard to do. This can be done with a molecule, but it's hard to do with a nanoparticle. So a very small nanoparticle is huge in comparison to the carbon dioxide molecule. So it's hard to tailor with a sub-angstrom precision the interactions with carbon dioxide. Molecules can be good catalysts. This is an example from Marc Robert in Paris, where he produces even methane, so an 8-electron product from CO2, with a photochemical systems with molecules. And he also made a cobalt phthalocyanine in a membrane electrolyzer, and with a very high current density, 200 milliamp per square centimeters. Sorry. With 200 milliamps per square centimeter, he could get the he could drive with a molecular catalyst CO2 reduction, and this is comparable to the best materials, silver and gold. So molecular catalysts can be competitive and probably outcompete many materials in the long run. So in SoFiA then, our idea is to use soap bubbles, a temporary and flexible gas compartment made from a proton-conducting mesoscale aqueous membrane stabilized by self-assembled surfactants. And the idea is that the membrane of the soap film could be a membrane where we separate oxygen evolution and CO2 reduction on different parts of the membrane. And a soap bubble, you may think, what is this? I was talking about durability. How durable is a soap bubble? No, it's true. Soap bubble is not durable, but it's very easy regenerative. It's self-assembled and is very easy to regenerate once it bursts. So this is basically the fundamental idea. Instead of using a very Formula One car that you spend a lot of time and money on making a very highly engineered interface, like the example from Caltech we saw. We thought instead of a simple transient and self-assembled membrane to do the separation that is needed. And in this membrane, we can tailor molecular components as photosensitizers and catalysts. So self-assembled system, regenerative and economic membrane, charge and product separation, and CO2 not limited by water solubility, because we are working at the interface between gas and water. So we're not limited by poor solubility of CO2 in water. And with that, I'd like to thank you for your attention and give over to the next speaker.
Well, introduction to our project and an overview on artificial photosynthesis. I'm now going to speak about the second part of our the second lecture in our workshop, which is the introduction to the SoFiA project. The project overview and critical aspects of the future and emerging technology grant writing. So myself, Indronil Sen, I wear two hats as a project manager in Uppsala University part-time, and also as a director of WASAB Innovations EOOD, which is a third party in the consortium and is based in SoFiA Tech Park incubator. So as Laif already said, solar photovoltaics is great, but there is a storage problem. There is a storage problem, and we need clean energy, and a viable solution is solar fuel by artificial photosynthesis, and renewable solar fuels like methanol, hydrogen, methane, carbon monoxide, etc. can be used as industrial feedstock and renewable solar fuels. So here I present the long-term vision in form of pilot projects. So this is what drove us to present a scalable and plausible project that is potentially a globally game changer in the field of energy. So here you can see that we had three different parts that we approached. One was to convert a brewery or a cement plant or a iron and steel plant into a hybrid artificial photosynthetic plant that uses solar fuel for its basic energy needs. Now note that a brewery or a cement plant, they produce carbon dioxide through not as a byproduct. So a brewery is producing carbon dioxide, clean carbon dioxide through fermentation reactions, and cement plant by calcination reactions. So these are two unique processes that can produce comparatively clean carbon dioxide. So these are our first case studies that we would want to implement our project in form of pilot projects. And when we develop our system, it can be added as an annex to this brewery or cement plant, and the CO2 from the flue gas through the technology can be converted to solar fuel that will gradually phase out the fossil fuel dependence on these industry. And then the surplus solar fuel, because it will again produce carbon dioxide by burning the fuel, and this carbon dioxide again is going to be recycled to form solar fuel. So there will always be surplus solar fuel after catering to the basic energy needs of this industry. This surplus solar fuel will be given to traditional companies. So we are interested in collaborating with traditional fuel companies that already have an established infrastructure, but in the infrastructure what is flowing is not sustainable. So what we are going to do is to empower them with sustainable tools and sustainable energy technologies. The other options are stand-alone artificial photosynthetic plant, and a third option is to use buildings as microenergy hubs. Using these three channels of solar fuels, traditional companies will feed green transportation and other use of these fuels, and also the same fuels can be used for industrial feedstock. So this was our long-term vision with which we approached our project. This has already been discussed by Laif, so I will skip it. The concept is that we looked into a soap bubble with different eyes. We looked at a soap bubble not as just a soap bubble, but we looked at it as something that can be utilized in high technology development. This slide has also been shared, and we are interested in photocatalysis at gas-water interface. So it is not in bulk, but we are interested in interfacial photocatalytic processes where the interface will have self-assembled monolayers and self-assembled of the photocatalytic systems that we are developing. At this point, I would like to shift the focus on 3 strategic pillars of our FET proposal, and I'm sharing this with colleagues and with peers openly so that the overall quality of grants and the overall quality of the projects can improve through proper project planning and through proper grant stage proposal preparation. So the first critical aspect of our project was to define objectives, and I'm sharing with you openly not the content but the context and the format of how this overall objective was presented in our case. So you see that there is an overall objective that we have, which was to develop a radical solar fuel innovations into a technology backbone of the global energy systems by 2030, and consequently strengthen the EU global leadership on renewables by establishing a pan-European consortium based on values of sustainable design, open innovation, inclusive, innovative and reflective societies, and highly cross-cutting international collaborations and use of stakeholders' knowledge. So you will notice that all of these, they contain keywords from the priorities of the European Commission, and they had been labeled, rather they had been marked in a blue font, and they had been in italics. So it is clear that we are addressing these. Second, please note that in the specific objectives, we not only define the objectives, but we define the key challenges, the associated key challenges, and the technology breakthroughs that are associated with those objectives, and we label them. You can see that we label them by developing some certain protocols, which is OBJM1, CHM1, the critical, the key challenges. Then we had the TBM1, so M1, M2, so on. You can easily follow what. So we divided the entire aspects of our proposal into 5 different categories, which was the materials, the technique, the prototype, the socio-economic aspect of it, and the commercial aspect. So we covered the entire range of the objectives, and what we did was label these so that they can be recalled later on, so that when there is an evaluator or the project management team, the steering committee, when they want to look at a certain objective or a certain key deliverable or a technology breakthrough, they can simply, on the description of action, they can search for these keywords and they will find, and over the entire description of action, these keywords will be linked. So this is one key aspect of our strategy towards preparing our proposal and the project. The second one, I want to a key aspect of the FET grant, that proposal that we wrote, I want to point out is the use of color coding. And this, we had used the color coding all throughout our proposal, but this is an example, which is a list of deliverables, and you can see that I have broken it down into 4 managerial, 17 scientific, and 14 dissemination and exploitation and communication actions. And then you can see that the dissemination and communication actions are labeled with a specific color coding, which is yellow. The management deliverables are in black, and the rest of it is in white, right? And then you can see how the formulation has taken place, the formatting has taken place in this chart, which allows not only evaluators but also us, the steering committee members, to correlate and manage the project very succinctly and efficiently. Now, in the date section and the final column, you can see that we have divided the entire column into 3 distinct parts with color coding. which represent the various the 3 different reporting periods. So the first reporting period is in 12 months, the second reporting period is after 18 months from the 12-month ends, and then the third reporting period is also after 18 months. So this is how our 48-month project was divided. And finally, I would like to share with you a key aspect of our proposal and our project, which was to develop a schematic similar to that of a PERT chart that shows SoFiA project at a glance, at one glance. And this really helps everyone, including the evaluators. So here we divide, first start with the foundation. So there can be many foundations. So here we have a foundation 1, which was chemical synthesis. And after the synthesis of the chemicals, you would disperse the functional dopants, and it would lead to, and then we had a second foundation, which is to fabricate a research and development platform. We had a bridge, the first bridge, the second bridge, a third bridge, and then a crossroad. So you can see that how the project planning is developing through foundations, through defining foundations of the project, the foundational tasks of the project, then defining different bridges, and then coming to crossroads, crossroad 1 and crossroad 2. And these crossroads are very important because they are also associated with the milestones of the project, because the crossroads are unique points which control a variety of channels and link different sets of work packages and tasks. Then we had finally the target. We had finally the target, and from the target we extended, because the PhET projects have to be foundational. So we extended to phase 2, and we have a bridge to phase 2 because it is a low technology readiness level project, and we would have to extend it to the pilot phase or a phase 2 R&D, and therefore we have this bridge to phase 2. And finally we have a final report, and that brings us to the end. So thank you for your attention, and I hereby end my presentation, and I request Professor Hai-Ning Tian from Uppsala University to give his lecture, to share his screen and give his lecture on polymer nanodots for photocatalysis. Professor Tian, please. We cannot hear him.
Okay, thanks, Indra. Thanks for inviting me to join this fantastic workshop. So good morning, everyone. My name is Hai-Ning Tian. I'm an associate professor in photoactive nanomaterials working in physical chemistry at Uppsala University. And today I will introduce one of our projects running in the group. So that's called the conjugated polymer nanodots for the photocatalysis. So today I will mainly talk about like production of hydrogen. Because why we want to produce hydrogen? So I think the hydrogen society is really promising. If you think about if we convert all of this energy or most of the resources on Earth to hydrogen, because the hydrogen has a really high energy density if you compare to the methane and the gasoline. So hydrogen, it has energy density almost 440 kilowatt hour per kilogram. So it's really good if we can store that into the hydrogen, and then we can use the hydrogen for the different purpose, transportation, or for our house. So we can convert this hydrogen by a lot of ways. For example, if you can convert solar energy to electricity, then you can use electricity to electrolyze the water, and you can get the hydrogen from water. Or you can use our electricity from grid to do the electrolysis. The same, you can get the hydrogen, or you can get the hydrogen from the biomass. Today, I would like to give another way, actually, most of the scientists now are interested in, that we call artificial photosynthesis. We use photocatalyst directly split the water into the hydrogen. So the photocatalyst, we are working on this dispersed photocatalyst in the water. So the one of this representative system is reported by the domain in Japan. And this system actually is mimic the photosystem. So in natural photosystem is like this scheme. We have the two nanoparticles, both absorbing light, but they both have the different valence band and the conduction band. For example, this one, the left one, is the tungsten oxide. It can get excited. The hole located in the valence band of the tungsten oxide can use to oxidize water. But for the right part, the titanium oxynitride, it can get excited and used hydrogen. If you combine these two systems with this scheme, then you can split the water, just use this dispersed photocatalyst system. But I have been working in organic functional materials for almost 15 years. So we are looking for some solution from organic chemistry. So if you think about organic polymers, so the HOMA and the LUMA of these polymers can be tuned by the different blocking units. You can use the different donor part or the acceptor part, or even you add more conjugated linker. You can tune the band gap, or you can tune the position of the LUMA and HOMA. Then you can use that for the different direction. For example, for the CO2 reduction, protein reduction, or you can use for the water oxidation. So if you compare these organic polymers with with this metal oxide, so what advantages would we have? It's quite easy to tune the band gap if you compare it to the organic, to the inorganic metal oxide. And also the synthesis is required low temperature, and these polymers is degradable. So that means if you don't want to use that, if you use the UV light to illuminate that, so this polymer will be decomposed, good for the environment. Photocatalyst reported actually it's a really long time ago, it's from the 1985 by the Suzuki Yanagita in the Osaka University. They report phenylene from this polymer is not that bad if you compare it with this sulfide. Yes.
Maybe change the network or something.
He's in. Now we lost him.
So we will wait for a few minutes, 2 or 3 minutes for him, and then we will continue. Please give us 2 to 3 minutes for him to log back on. Thank you. Hello everyone again, welcome back. Professor Tian has some technical difficulties, most probably because of the internet outage at where he was, most probably at the university. So we will carry on with our program and going to the next presenter, and we will wait for Professor Tian, and at the end of our presentation, if he is back, then we will have him again from where he started. Meanwhile, also it is possible that we can accommodate his presentation tomorrow if it is possible. So please, thank you for your patience, and we will move on to artificial photosynthesis in liposomes, Professor Sylvestre Bonnet. Professor Bonnet, if you can kindly share your screen, and we will go ahead with your presentation. Thank you.
Indra, can you see my screen now?
Yes.
Yes, thanks a lot for the first very useful for me, as several topics have been introduced already. I would like to focus on liposomes and comment a bit on the link between liposomes and soap bubbles and soap films, which you can see a nice picture of, which I took in Basel a couple of years ago. You have heard from Professor Hammarström that we are trying to mimic in the SoFiA project photosynthesis and the natural photosynthesis, which is taking place, for example, in green leaves and small organelles that are, well, basically taking electrons from water in the plant to put into a small molecular shuttle, which has a name, so it's NADPH. So this is basically a molecule that is dragging electrons and protons that are going to move away to reduce CO2. And in that process, which is called water oxidation, the leaf, the green leaf or bacteria, they release dioxygen, which we breathe, but on a photosynthetic point of view, it's a waste. So the idea of a leaf is that it's a membrane, and soap bubble, when we gathered to make the SoFiA project some years ago, we realized that a soap film is also, in a way, an interface, and that if we would be able to organize molecules and photoactive molecules at the surface of a soap film, so within a soap bubble or within a device that generate these things, it might be possible to realize artificial photosynthesis, so to mimic the process of natural photosynthesis, but using a membrane which is artificial, which is relatively short-lived, but we have soap films now in the lab which last 30 minutes or even 1 hour, while some of the proteins involved in natural photosynthesis, they are also renewed every 30 minutes. So the fact that you need to renew your photocatalytic systems every now and then when you're doing photocatalysis is actually something which is very well used also by nature. So you've seen another picture from that natural photosynthesis system by Leif. What I wanted to focus here is not the fact that it's very complicated. You see a lot of different proteins embedded in a membrane, but I would like to insist more on the fact that the whole system is actually embedded in membrane, because that's what we're going to talk now. So on one side of the membrane, water is being oxidized by a catalyst, and you see the electrons more or less is going to the other side of the membrane. So we need to split electrons, well, move electrons away from one side of the membrane to the other. And to do that, nature, well, needs many quite complicated protein systems, which are embedded in a membrane. So there's a few questions here which I wanted to address today. So one is, why is nature using lipid membranes for doing photosynthesis? The other one is it possible to functionalize artificial lipid membranes with photoactive molecules? I'm going to focus the talk today on this. So a correlate of this is whether it's possible to make a photocatalyst molecule, or either catalyst or photosensitizer, SOPI, which is a strategy we are using in the SoFiA project. And then can we use these SOPI molecules to functionalize soap films, because the SoFiA project is about soap films. So if we look at a biological membrane here in green, we will see that it's made essentially of lipid molecules. So lipid molecule is made of essentially two parts. So you can model it as a two-part. There is a polar part here, which is, you see, full of oxygen and nitrogens. And there's an apolar part, which is, often some alkyl tails. Sometimes they are slightly unsaturated, but they are hydrophobic. And when you put these molecules in water, they have a tendency to form a bilayer, to face the polar head to the water side, and the hydrophobic part to put them together so that they don't see the water part. Now, this is a little bit what a membrane looks like. You see the lipid bilayer over there, and there's water on both sides because you have hydrophilic heads on both sides. Now, if you go to soap film, it actually is quite similar, because 1/2 of the previous picture, we keep it. A soap film is a film of water, but at the interface with air, for example, when you make a soap bubble, or with gas, for example, CO2, where we make a soap film in the SoFiA project, you see that we also need some form of surfactant molecule, which are stabilizing the interface between water, which is essentially polar, and the gas phase, which is much less polar. So usually the molecules in a soap film are going to show their polar head to the water side, and the apolar tail to the gas phase, which is less polar. So now the question is, if we would like to functionalize such a soap film with photocatalytic molecules, how can we do? And one of the things that we are exploring in the SoFiA project is actually to use a photoactive molecule. So here's is a metal-based photosensitizer. And you see we have functionalized this molecule with alkyl tail, with the idea that the alkyl tail are hydrophobic, so they would actually mingle with the surfactant bases just because they like each other and they don't like water. While the photoactive part of the molecule would lie somewhere at the interface between the water phase and the monolayer. And the monolayer is very, very thin. And so we are talking about 2 nanometer here, something like that. Which means that we are really looking at interfacial mechanism. And if we can organize all these molecules the same way as what nature is doing for natural photosynthesis, that we might be able to realize an artificial photosynthesis system. So you see here now that there is actually a link between a soap film functionalized with soapy molecules and a lipid bilayer, which is basically a double soap film. More or less, it's not exactly the same, but you can see that it is possible to functionalize also lipid bilayer as a model of soap film. So who is the model of who? Well, here we are using membranes as a model of soap films. But we use the same molecule, these soapy molecules, to insert in the lipid bilayer and make it photocatalytic. So how to work with these membranes? Well, we work not with flat membranes, what I showed you up to now, but we're working with these liposomes, which are a spherical lipid bilayer, and we insert these photoactive molecule in the lipid bilayer inside, and we have an inside compartment and an outside compartment to organize electron transfer. So if you compare liposome and soap films, they look like each other, but they are not exactly the same. What you see is that the liposome has water in and water out, while a soap film monolayer has water one side and on the other side is gas. Another thing that you might not directly see on that scheme, but that is quite important, is that there is a significant higher surface to volume ratio when you're working with liposome, because you can have a lot of liposome in a solution. So if all these liposomes have the same doping concentration as what you have on the right, you can actually generate much more surface in the liposome than in a soap film, where basically the surface of your soap film is the surface of your interface and not more. While here we can really have a much higher surface. So because of that higher amount of surface, so to say, in liposome sample, we make more photocatalytic product, which is a bit more easy to detect, and that's why we have been starting working with this. Another thing is that liposome essentially don't burst like soap films. Even if so, as I said, soap films can be stable up to tens of minutes, 1 hour, 2 hours. They are obviously mechanically sensitive. So now we want to do photocatalysis. So if we look in a homogeneous system, we have we need a couple of photoactive elements. So here for doing water oxidation. So the water oxidation allows you to get electrons. And you see you need a photosensitizer that is going to grab the energy of the light. So you get an excited state. We also have water, which we need to oxidize to get its electron. We need a catalyst to do that water oxidation. And we need a shuttle to get the electrons and bring them to the side where CO2 reduction is going to happen. So ideally, you irradiate the photosensitizer, it gets excited, then just charge separation, it will move one electron to the electron acceptor or the electron shuttle here, become oxidizing. By become oxidized, it becomes oxidizing. So it's going to get an electron from the catalyst, which becomes oxidized itself. And when you do that a couple of times, you will end up, and if your catalyst is a good water oxidation catalyst, then you can oxidize water into oxygen and protons, and you will recover your catalyst, and you can go through the cycle again. So basically, you're going to generate electrons and protons. So this is the system, homogeneous system. Another way to look at photocatalytic water oxidation is in kind of a plant, pipeline kind of look. You feed your system with water because that's where you want to get the electrons from. You have a photosensitizer tool. You need some light and an electron shuttle. When you put all these things together, you generate some PS+, which is the oxidized version of the photosensitizer. Then the catalyst is going to give an electron to PS+. So you oxidize the catalyst with PS+. So your next species here is the oxidized catalyst. And then you have a catalytic step, which does the water oxidation itself. And what is important in these processes is that you have a decomposition of your molecules is always possible, whether you are working with molecules or materials, you have decompositions. So you see that you can decompose the photosensitizer, decompose the catalyst. And when you do that, of course, you're going to limit the outcome of your product and the amount of electrons that you can isolate and get for making solar fuels. So one of the very important questions in photocatalysis is what limits the stability of the system? How many times can you do water oxidation or CO2 reduction? One of the problem also is you see there are 3 steps here, the generation of PS+, CAT+, and water. So they have different rates. And sometimes one of these rates is limiting. And for a long time, the 3rd step here has been rate limiting because the catalysts were not good enough. So one of the questions is, are the catalysts that we have now good enough for water photooxidation? And of course, what limits the rate? If you want to make a lot of solar fuel, you will have this reaction needs to be fast enough. What happens when you put all these molecules in a liposome or in a soap film in terms of mechanism? So what we started with is to look at water photocatalytic oxidation in homogeneous conditions with a ruthenium catalyst, which is called ruthenium BDA bispyridine, and a ruthenium photosensitizer in presence of peroxodisulfate as an electron acceptor at pH 7. What we realized was that the limiting step for this system was actually the electron transfer from the catalyst to the oxidized PS+. So it's the 2nd step of this global view of photocatalysis. While for a long time, people had thought that it was the 3rd step that was limiting the photocatalysis. In homogeneous solution, it's often, not always, but it's often the 2nd step that is limiting. Now we wanted to see what happens when you make this reaction on liposome. So we started with, this was our photosensitizer. And as you can see, you can functionalize one of the ligands that are coordinated to the metal. So you have a photosensitizer without functional group, which we use for homogeneous solution. When you put these long alkyl tails, then you get a molecule which you can insert into a lipid bilayer to make photocatalysis. We do the same for the water oxidation catalyst, also here, long alkyl tails. This is a catalyst, this is a photosensitizer. Then we have to, well, it's important to realize that to do that, you need to have good chemists. So in the first year of the SoFiA project, we hired an excellent chemist from Germany who now started a position in Ulm. And she made this family of molecule. You see, you can start with the ligand, which doesn't have the long soapy tail over there. You deprotonate that, then you add an alkyl bromide, and you add the tails over there. You can do that. Then once you have your ligand, you have to bind it to the ruthenium center to make your final molecule. And you can also change the counter ion, which is the ions that are well, compensating for the positive charge of the catalyst. So she made a series of molecules with different length to see, well, how to study also how the lipid bilayer can be functionalized. Once you have these molecules at hand, you need to make your liposomes. So liposomes are made of lipid molecules. You mix these lipid molecules with the soapy molecules I've just shown you. And then you need students. So here an Erasmus student, and they are going to push through the solution containing all your lipid-like molecules and soapy molecules through a small filter. At the end of the game, you get a colored solution because the molecules absorb light. And if you would look with an electron microscope, for example, you see that you have nice liposomes with a surface here, which are represented schematically here, which is functionalized with your soapy molecule. And we are talking here about liposome, which are typically 150 nanometer, although you can modify the size, but we were working with 150 nanometer. Then you need to shine light on these things. You can see here the kind of photoreactor we are using to shine light on liposome. You have a LED on the back here, which is shining through a solution which contains the liposome. We have a stirrer, and we have a system of sensors to detect the oxygen you're making, and GC also to quantify the amount of oxygen that you make. And I'm going to just show you briefly the 2 types of results. The first one is to answer the question of whether the catalysts that we have are good enough. And what you can do on this kind of photocatalytic liposome is to change the light intensity So you can see here, this is the amount of light that the sun on average is giving on Earth. And we modified the amount of light that we put on our system. And what you see is that in the domain, let's say, that is below that limit, the rate of production of oxygen is actually proportional to the light intensity, which maybe seems logical for people because we are doing photocatalysis. On the other hand, everyone was expecting for a long time that the catalyst is always limiting water oxidation, so that the amount of light you would put would not matter too much. But as you can see, it really matters, which means that the catalyst actually fast enough. And here I see this for two different types of liposomes, one which has the ruthenium catalyst I've shown to you, and a ruthenium photosensitizer. But also we have changed the catalyst for cobalt-based catalyst, and we had a similar trend over there. So we do have nowadays catalysts that are good enough for water oxidation in a photocatalytic system. Now, another type of effect of the liposome I wanted to mention was the question of stability. If you look in a homogeneous system, so without any liposome, just you put the catalyst, not SoFi, put them in solution, and you you increase the light intensity, what you will see is that this number, the photocatalytic turnover number, which is a measure of the photostability of your system, goes down when you get more and more light. So we understand that now relatively well, but it's important to realize that, well, if you put something on your roof, you would like that your photocatalytic system works also when there is a lot of sun or a little bit of sun. So this dependence of the stability of your system on light intensity is not something very good. And we've seen it with three different kinds of water oxidation catalysts. Now, when you look at the liposome, we changed the light intensity actually in a larger scale. And what you see is that the stability of our system becomes very constant, also with two different types of a catalyst. So our liposome photocatalytic systems are less sensitive to decomposition at high light intensity compared to homogeneous system, let's say. So this is an interesting effect, and we understand it by realizing when you put the catalyst and the photosensitizer on the lipid bilayer, put them very close together, so that the second step, which we said in homogeneous solution was rate limiting, becomes much, much faster just because the molecules are super close from each other. So electron transfer is very fast. So now our rate determining step becomes the first step. So the generation of PS+. This is the slow step of the whole photocatalytic process, but this is very fast. And as one of the main decomposition pathway is decomposition of the photosensitizer, if you accumulate a lot of PS+ over there, you will have a lot of decomposition, which is happening when you are in homogeneous solution. But in liposome, this is going to react very quickly with a catalyst and disappear from the membrane so that it does not decompose and it can do another cycle. And that's one of the reasons why we are less sensitive to the changes to the change of intensity in terms of stability of the photocatalytic system. So this is a short talk today, so I won't take too much of your time. I just wanted to come back to the link between liposome and soap films. So in both cases, we have surfactant-like molecule. You take photoactive molecule, you functionalize it with a soapy tail, and you get a soapy molecule. And these soapy molecules, you can use them in lipid bilayers to functionalize liposomes, or in soap films to functionalize soap films. So there is a strong connection here. We are generate by working at the interface, by concentrating all our molecules at the interface, we are going to get higher local concentrations. And what I've shown to you today is that this changes of local concentration changes quite dramatically the effect that you see from outside. When you look at the performances of your system, you see that the kinetics is changed, the stability is changed, the mechanism is actually changing. When you compare to homogeneous conditions, which we are also expecting with the soap films. I want to finish just by saying that we have been developing in the last year a system to study photocatalytic soap film, and here you see a couple of pictures. That's the setup we have end up with. You see the soap film is going to be here in a hole, and we can feed this system with different gases, which we can analyze, and then my new postdoc, Agnès Amati in Leiden, has started to shine light on these soap films. And we are now studying whether we can make oxygen in these soap films, and we are also working on going from ruthenium to first transition metals, because we need more, well, let's say less scarce element for our system if we want to be more sustainable. So I'm going to stop here, give back the floor to Indra, not without thanking the two postdocs in my group who have worked on this project, Andrea Panwitz, who is now gone, and Agnès Amati, who from the SoFiA project, which is one of the most challenging but also enthusiastic projects I've ever worked with. Thanks to Indra for organizing this symposium today, and I give back the floor to you.
Thank you so much, Silvestre. Professor Tian probably is online now. And Heining, I request that if you can start your presentation again. Thank you.
Can you hear me now?
Yes.
Okay, thanks. Sorry for this the network problem. Okay, so thanks again, Indra, for inviting me for this workshop. So today I would like to introduce one of my projects running in my group. It's conjugated polymer nanodots for the photocatalysis. And today I will mainly talk about hydrogen production in this project. So why we need hydrogen? So I think the hydrogen society is proposed from this hydrogen in Europe is really promising, because the hydrogen has a very high energy density if you compare with the methane and the gasoline. So the hydrogen has almost 40 kilowatt per kilogram the energy density. And if you use the hydrogen, the byproduct is only the water. That is really environment friendly. You don't create any carbon dioxide, the greenhouse gas in this case. And how to get the hydrogen? There's a lot of ways to do that. You can get the hydrogen from the biomass, or you can get the hydrogen from the electrolyzer. You use electricity. This electricity can be generated from the renewable energy. Sunlight, you use the solar cell, the wind power, or you can use some like the thermal power to generate the electricity to do the electrolysis. Even the electricity generated from our grid, you can use that for electrolyzed water into the hydrogen. So then the hydrogen can be used for a lot of things, so transportation in our day.
Hello, Heining, your connection again is broken. There is this technical problem. You're frozen. I do not know if you can hear us. Unfortunately, there is a technical problem again. We'll wait for 2 more minutes to. Did he log out or still there? No, he lost connection. Right? He's not connected. Yeah, so we'll have.
Yeah, no. He texted me. He need to. It doesn't work. He's not working from university, so his internet is apparently very unstable.
Okay.
We have to give up on that today.
Yeah, unfortunately, we'll have to move to the next lecture by Dr. Yusrat Timune, which is about soap foam analysis using techless instruments. Dr. Timune, can you kindly share your screen and start your presentation?
Sure. Hello everyone, can you hear me?
Yes.
Can you see my presentation? Okay, great. So hi again, everyone. So I'm Yusra Timune. I work at Techless Scientific, and today I'll be talking about the company Techless and also our expertise in characterizing liquid foams and interfacial phenomena. Okay, so I'm going to start with a few words about Teclis. So Teclis is a French company that has 25 years old, and it specializes in scientific instruments for interfacial phenomena. And as I said previously, its area of expertise is the characterization of the physicochemical properties of interfaces between fluids and the characterization of liquid foams. So in practice at Teclis, we design, manufacture, and commercialize instruments to characterize interfacial phenomena and liquid foams. And we have two main instruments. So the foam scan, which is a foam analyzer. These instruments can be used to characterize the macro scale properties of a foam, such as the foamability of a solution, for example, also the stability of a foam, and also the liquid fraction. And then also the second instrument that is commercialized is a drop tensiometer. So in this case, we can use these instruments to characterize the properties at fluid-fluid interfaces. So we could look at things such as surface tension, elasticity, and things like that. Okay, then I'm going to present briefly the collaborators Teclis works with. So first, we have a lot of academic partners in different groups all over the world. So here I'm showing some examples of ongoing research projects. So of course, we have the SoFiA project. Then also we have another project with the CNRS, which is a French research institute. And for example, in this one, we are looking at the lipid protein interaction at interfaces. Then another one, for example, is between multiple companies and also an academic partner. And this one is about the hydrodynamic of fluid foams. Then, obviously, we also work with industrial companies, and in this case, they are in very different sectors. So, for example, chemistry, cosmetics, food and beverage, oil and gas, and also many others. Okay, so after this brief description of the company, we are going to move to science. And in the following, I'm going to start by presenting a few basics about soap foams. And then in the second part, I'm going to explain how the instruments commercialized by Teclis can be used in order to characterize and understand better these systems. Okay, so liquid foams can be found and are used in very different applications. So for example, food. So we can find foams in beers, in desserts, in, these kind of things. Then we can also find foams in cosmetics and detergency. We find them also in civil engineering, where they are used to enhance the insulation properties of concrete. And they are also used in many different industry in froth flotation, for example. And the reason behind this widespread use are the advantages that liquid foams have. So first, they are lightweight, which makes them very easy to handle. They also allow to use less raw materials. So for example, for a fixed volume of the final product, we are going to use less raw material if we add a gas phase. And they also have very interesting expansion properties. So in this case, this is very interesting for firefighting foams, for example. And liquid foams also provide elasticity. So this is important for cleaning products, for example, because when we apply them, for example, on a surface, we don't want them to flow immediately. We want them to stay there. So, yeah. Okay, so now that we have seen a little bit where liquid foams are used and why, we are going to take a step back and define what is a liquid foam. So a liquid foam consists in a suspension of gas bubbles in a liquid continuous phase. So here I'm showing pictures of different liquid foams, and Obviously, what you can see is that a liquid foam can have different aspects. So in this first picture, for example, we have a monodispersed foam, which means that all the bubbles have the same size. Then in this second picture, we have a polydispersed foam. So we have very different sizes in terms of the bubbles. Then the aspect will also depend on how much liquid is trapped inside the foam. So for example, in this one, we have an extremely dry foam. And then what you can see is that it has these angular aspects and all of the bubbles are extremely deformed. Then the last example is showing a wet foam, and in this case, the bubbles are rounded. Okay, so as we have seen, the structure and the aspect of a liquid foam is going to depend on a few parameters. So the first one being the liquid fraction, so the quantity of the liquid that is trapped inside the liquid foam. The second one being the polydispersity or the monodispersity of the foam. And the last one is the order or the disorder inside the foam. So if we know, for example, these three parameters, we are able to predict the structure of a given liquid foam. Okay, so then if we spend some time looking at a liquid foam, we realize that foams are multi-scale systems. So at the scale of the foam, so at the macro scale, foams are mushy materials. So they are somewhere between a rigid body and a liquid. So if we want to be precise, they are Bingham plastic fluids, which means that they are going to flow if we apply a stress that is above a given threshold value. So that's for the macro scale. Then if we look more closely into the foam, we are going to see all of the bubbles that are composing the foam, and we can also see the very thin liquid films that are separating bubbles. Then at an even smaller scale, we see the interfaces between the gas and the liquid phase. The thing that is important here is that the properties of the foam at the macro scale are going to depend on phenomena that are happening in all these different scales. So liquid foams are systems that are very rich and very complex to study. Okay, so another interesting properties of liquid foams is that they are transient systems. So that means that their lifetime is limited. So eventually all of the liquid foams are going to disappear at some point. This is basically due to the fact that creating liquid gas interfaces costs energy, and the equilibrium states correspond to the state where we have the least amount of these interfaces. Okay, so in order to make foaming easier and in order to lower the energy that we need to input in order to create a liquid foam, surface active molecules or surfactants are commonly used. So first, by absorbing the liquid gas interfaces, they help stabilizing the newly created bubbles. And then also by providing elasticity to these interfaces, they help the very thin liquid films that separate bubbles to heal in case of a stretching, for example. So this is what we refer to as the Gibbs-Marangoni effect. So then soon after the formation of a liquid bubble starts the aging or the destabilization phase. So three main mechanisms are responsible of this aging. So the first one is the drainage. So here basically the liquid flows towards the bottom of the foam due to gravity. And the result is a foam that is extremely heterogeneous. So in the top, we have this very dry foam that is angular, as we've seen previously. And in the bottom, we have this very wet foam. Then the second mechanism responsible of the aging of the liquid foams is coalescence. So it corresponds simply to the breakage of a thin liquid film that initially was separating two bubbles. And here again, surfactants or surface active molecules actually can play a role in stabilizing liquid foams against coalescence. So if we imagine two interfaces that are laden by surfactants. So for example, if these surfactants have a charge, then we are going to have an electrostatic repulsion between these interfaces, which will stabilize this liquid film. And for example, if we simply have protein in these proteins at the interfaces, we will have a steric repulsion that will also stabilize thin films against coalescence. So then the last agent mechanism is the Oswald-Rippinen. So it corresponds to the fact that in the very small bubbles, the pressure is very high because the curvature is very large, which means that the gas will tend to move from the small bubbles to the large one because of the pressure gradient. Okay. So now after these generalities about liquid foams, we are going to see what are the right parameters to look at if we want to characterize a liquid foam. But first, so as we've seen, liquid foams are multi-scale systems. So if we want to really understand and characterize liquid foams, we need to do a characterization at different scales. So the first scale we need to look at is the scale of the foam. And in this case, there are a few parameters that give us very important information about the behavior of this liquid foam we are looking at. So the first one is the foamability of a solution. For example, if we inject during a given solution, the thing to look at is what's the volume of foam we have been able to produce. Then we could look at the foam stability by just looking at how the foam is evolving over time. And then we can also look at the liquid fraction, again, during time. And the last thing we can look at is the structure of the bubbles. For example, if they are monodisperse, polydisperse, and also how their size is evolving with time. Okay, so that's for the scale of the foam. Then, as we've seen a couple of slides ago, the properties of the liquid-gas interfaces that are present inside the liquid foam have an impact on the properties of the liquid foam itself. So it's really important to characterize the properties at the scale of one single liquid-gas interface. So in this case, the two things we can look at are the surfactant absorption. So for example, we can simply follow the evolution of surface tension as a function of time. And then it's also important to characterize the elasticity of these interfaces, because as we've seen previously, they can really help stabilizing liquid foams. Okay, so now we are moving to the practical part, I guess, and we are going to start with the characterization at the scale of the foam. And in this case, the Techlist Foam Analyzer is a great tool to get valuable information about the behavior of the liquid foam of interest we are studying. So just a few words about the setup that is presented here in the center. So it consists in a column of glass where foam is generated. Then thanks to a first camera, we can get a macro view of the foam, which allows us to follow the foam volume over time. And also thanks to different two electrodes that are placed at different positions in the column, we can also follow the evolution of the liquid fraction over time at different positions. Then we have also a second camera that zooms in a little bit more on the foam. And with this second camera, actually, the things that we look at are the bubbles. So what we can see is, for example, the size distribution of the bubbles and also how the size distribution evolves over time. Okay, so let's start with a first example of the results that we can obtain. So here, what I'm showing is the foam volume over time for 3 different samples and also the corresponding videos, but I guess that went too fast. But anyway, so here we have a first stage during which the foam has been generated. So here what we can say is that the 3 samples have the same foamability. So if we foam for a given time, then we're going to obtain the same volume of foam at the end. Then once the foaming process is stopped, what we can see is that sample C is extremely unstable. So the foam volume decreases very, very quickly, while sample A and B seem to be more stable. Okay, so these are the kind of information that are quite useful if we want, for example, to get a foam or to produce a foam with given properties. So then let's move to this second example where we show where we are looking at the scale of the bubbles, actually. So these are again videos showing the structure of the bubbles for 3 different samples. And here the 2 plots show the number of bubbles versus time, and then also the mean bubble radius. So these kind of information are actually quite important because they allows us to know, for example, which is the aging mechanism that is dominant in a liquid form, because, for example, coalescence and the Oswald-Reppinen both have some kind of signature behavior. So by following, for example, the mean bubble radius evolution and also the number of bubbles, we can define the aging mechanism that is responsible of the destabilization of our foams. Okay, so now we are moving to the second scale, which is the scale of liquid gas interfaces, and the properties that we want to know, or the properties that we want to characterize at this scale, are the adsorption speed of surfactants, and this is possible simply by looking at the surface tension versus time plots. Some other interesting properties are the CMC, which is the critical micellar concentration. So it's basically the concentration above which micelles starts forming in our solution. And also the third very interesting properties is the interfacial elasticity. And this is possible through oscillatory experiments. So imagine a bubble or a volume that where the volume is oscillating, basically. So by tracking the evolution of surface tension and area during this oscillation, we can deduce the interfacial rheological properties of these interfaces. Okay, and in order to achieve all that, we use a drop tensiometer, and the technique is based on image analysis. So we start from a bubble or a drop, and then by extracting its shape and fitting it with a Laplacian profile, we can simply deduce the surface tension. So it's basically the fitting parameter. So that's how we obtain the interfacial properties of liquid gas interfaces. Okay, so this is an overview of all the possible characterization that we can do at the scale of a liquid gas interface. So as we've seen, we can obviously look at surface tension at different interfaces. So water, air, oil, air, for example. We can also look at the interfacial activity of the molecules, like nanoparticles, proteins, for example. We can also probe the viscoelastic properties and deduce the viscoelastic moduli. We can also look at the compression isotherms and things like that. So anyway, a lot of things to do at the scale of one single liquid air interface. Okay. So before summarizing, I just wanted to show an example of the plots that we can obtain with a Tegy's drop tensiometer. So here we have surface tension as a function of time for different concentration of C12E6 solutions. So C12E6 is a non-ionic surfactant that we have been using in the SoFiA project to stabilize soap films. So it is a commercial surfactant, and so these plots give us a lot of information. So obviously the first one is the minimal surface tension that we can reach, but then also thanks to these plots, we can deduce the critical micellar concentration. And then after, if we do some fitting, we can also deduce information such as the size of these molecules at the interface and things like that. Okay. So to summarize, we have seen that foams are transient and multiscale systems. We have also seen that the interfacial properties play a very important role in the forming process, and that these properties can be characterized with a drop tensiometer. And finally, we have seen that a multiscale characterization is needed to probe the stability and of liquid foams. Yeah. And also, yeah, basically, yeah, that's it. I'm done. Thanks. Yeah, here are the references. So just in case you need that.
Thank you, Dr. Timune, for this excellent presentation. I see that Professor Tian is there, and maybe he has a different internet connection. So we can try one last time to see if he can show us the presentation. Professor Tian, please.
The problem is this network is still unstable, so I'm not sure. We can try the last time.
We can you can turn your video off, perhaps that can help.
Great, I can try.
Yes, thank you.
Give me seconds. I have adjust. Okay, great. And okay, so I also change it to
PDF form.
yes, PDF file could be saved somewhere. I need to find how to put this full screen. Let me check. So I will try the PowerPoint. It's I think it's fine. Okay, so can you see my PowerPoint now? No. Yeah, but I think the PDF has some problem. I also have. Okay, now.
Now we see
this. Great.
Yes.
Okay, so I start from beginning. So I will introduce these conjugated polymer dots for the photocatalysis. Today I will mainly talk about the hydrogen production based on these P dots. So we want to have this hydrogen because this hydrogen has high energy density, because we can use that as almost energy environmental friendly energy carrier, because it does not produce any byproduct if you use that. So the water always is a byproduct in this case. So it can be generated from the different resources, as I mentioned before. So I skipped this one to make sure I can go to my main content this time. So for the photocatalyst, we can use that to directly split water into the hydrogen. And this one of the representative work reported by the domain from Japan. Actually, they can mimic this scheme from natural photosynthesis. They use two light harvesting materials. One is tungsten oxide, another is titanium oxynitride. So tungsten oxide can get excited. So the holes located at the valence band of the tungsten oxide can be used for the water oxidation. And if you excited the tungsten oxynitride, the electrons located in the conduction band of the material can be used for the proton reduction. Then you use a redox mediate to link these two systems together to form this scheme. Then you can do the full word splitting. But I have been working on the organic functional materials for 15 years. I'm always looking for solutions from organic chemistry perspective. If you think about organic polymers, so it also have this band gap between the HOMO and LUMO, but this band gap can be tuned if you use different blocking units. For example, you use different donor, and you use different acceptor, or even you add the different conjugated linker. Then you can tune this band gap. You also can tune this LUMO and HOMO position. Then you can use this for different reactions, for proton reduction, from the luma, from the water oxidation, from the HOMO. You also can tune this luma level for the CO2 reduction. That another advantage for the organic polymers, because when you synthesize organic polymers, it does not require the high temperature. So you always had 100 degree, you do the pseudo coupling, you can get the polymers. And this polymer also is environment friendly. If you don't want to use that, you illuminate that with the UV light, and it will be decomposed to the small chemicals. And first, the polymer for the catalyst is reported by Suzu Yanagida from the Osaka University in 1985, which is a long time ago. And this is polyphenylene for the catalyst. If you compare this catalyst for the proton reduction with this thing called sulfide for the proton reduction, actually it's not that bad. So it works quite well. But only the problem for this phenylene, polyphenylene materials, because its absorption is not that good. So the maximum absorption around 300. There's some little absorption in the visible region. So that is not really good for the catalyst, because most of the energy located in the visible region and also some in the near region of the solar spectrum. So in 2009, so there's one paper published by the Xincheng one. It's about this graphic carbonitride materials. It can absorb the visible light around 400 nanometer. And it's good for the water reduction and for the proton reduction. It has to add some co-catalysts like platinum. And in 2015, there's some like mesoporous polymers reported by Andy Cooper from the Liverpool University in the UK. Actually, you can tune the different units. Then you can get different color of these materials. They can absorb the different region from the solar spectrum. And if you check this 442 catalytic experiment with this kind of materials, you can see this is a reactor. So you can see these particles, these are polymers. The problem is because these polymers, they are highly hydrophobic. You have to add some organic solvent in there to make sure they can be dispersed well, but still you can see by eyes these big particles. But what's the problem if there is big particles? If you think about there's particle 1 micrometer, so this is typical the size if you do this kind of the water organic solvent mixture dispersion system. So you have the 1 micrometer particle size. But if you think about exciton diffuse length from the organic polymers, so it usually, if we take the example from the P3HT, this is one of the popular organic polymers used in organic solar cell. So you can get this diffuse length of exciton in this P3HT materials is 10 nanometer to 20 nanometer. That's what happens if you have a 1 micrometer size. So if you illuminate this material, you generate exciton at the center. So this exciton needed to diffuse almost 500 nanometer to the surface that is the site for the reaction happening. It cannot go to a surface, then it emits the light. So let's go back to the ground state. So only the exciton nearby the surface here, it can move to a surface and to do the reaction. Then in this case, what's the problem? So most of the light generated exciton in these particles actually are useless. You just consume the light, you excite the exciton, but then you did not do any photocatalytic reaction. And also it's difficult to get a reliable stability test. So sometimes you see the paper published, they do this, a lot of cycles, you can see the system quite stable. But if there is only 1% of this particle, it works in the system, so it only is 1% decomposed within 1 hour. So actually it's hard to evaluate the stability. So actually you just consume your material because you have a lot of materials to be consumed. So that's why you say it's quite stable, but I don't think that is a good way to do that. So what happens if we make the polymer particle smaller? So if you think about how to make this polymer particle smaller, so there is one way we call the nano precipitation method. It's not I invented. It's this is invented by a long time ago, so in the biochemistry applications. So you can use the polymers here, like a PFBT polymer, and you use another amphiphytic polymer. So you dissolve them in organic solvent, then inject that into water, because this polymer will be self-assembling each other. Then you slowly remove the organic solvent, so they will shrink, they will aggregate. So the hydrophilic part will point out to the water, so you form a stabilized P dots. This is called polymer dots, but this name also is popularly used in the biochemistry. You can use these P dots for this as the fluorescence probe to do a lot of biochemistry application. But when I check these polymer dots, actually, if we use the FBT P dots, if the HOMA and the LUMA, so the LUMA actually is a 1.0 volt versus normal hydrogen electrode. It can be used for the proton reduction. It's thermodynamically feasible to reduce proton to the hydrogen. And so we prepared the P dots, the PFBT P dots in our lab. It has the 40 nanometer particle size. If you think about if this material has 20 nanometer exciton diffusion length, that almost all of the exciton generated in these particles can be used for the photocatalysis. So we did first this photocatalytic experiment. You can see when we give the light, we use ascorbic acid as a sacrificial donor. When we give the light, you can see the hydrogen produced. When we switch off the light, it's stopped. We give the light, it's on again. So this is the light-driven process. So we get the high hydrogen is quite good, but without P dots without P dots and without ascorbic acid, we do not see any hydrogen generated from this system. And the problem we can see is before we have P dots, but after, so the P dots get aggregated. When these P dots get aggregated, it does not work at all now. We also compare with the pristine polymers. It's not polymer dots, that's just polymer put in water, the same amount as compared in the P dot sample. But you can see here the hydrogen we generated is -5. Here it's 3.0. So it's almost, if you use the P dots, it can generate almost 6 orders of magnitude hydrogen from the system. So this is really efficient. So the questions left for us, so where is the reactive site in this polymer? Because we did not add any co-catalyst, no PT platinum inside. But of course, the synthesis of the polymer from Suzuki coupling, so it has that PD. This could be radio maintained inside, or it could be the organic unit. And also another question is how to improve the performance and the stability of the P dots for the catalyst. So if you think about the structure we talk about with the PFBT, we have the donor, we have the acceptor. The acceptor is the thiodiazole unit. We get excited, you have the electrons located at the BT part. If you reduce that, electrons still on the BT part. So if you think about the electron here as the reduced state is used for the proton reduction, then we assume we can hypothesize that BT could be the active site. So we will talk about this more later on. So we use the different polymers. So this PFBT, and we also use the PFODTBT, that this one with 2,000 units compared with the polymer 1. And the polymer 3, we just get rid of this BT units. We don't have the BT units in this polymer now, but we prepare the P dots. They all have the same, almost the same size, and the polymer 2 has a really red shift absorption. So we expect it can give high hydrogen production from these polymer dots. And from the energy level, all of the polymers can thermodynamically reduce the proton to the hydrogen, and also can be reduced by the sacrificial donor. But from the photocatalytic test, if you can see here, the polymer 2, the P dots 2, as we expected, it gives much higher hydrogen production as compared with polymer 1. So that is first polymer we used. And without the thiodiazole unit, the BT unit, we see very slight amount of hydrogen produced. So that means this BT part is really important in this case. So if you think about the polymer 1 and the polymer 3, they two have almost a similar absorption. Thermodynamically, it is possible to reduce protein, but the polymer 3 does not work. But polymer 1, it works much better than polymer 3. So we conclude the BT unit is very important. So this is the quantum yield, but why the polymer 2 is much better than the polymer 1, because it absorbs much more this red region light from the solar spectrum. You can see we have the quantum yield of 0.6% at 550 nanometer for the p-2, but there's almost nothing for the p-1. So that means if you tune the structure of the polymers, it can be to improve the photokinetic performance. So you have to adjust the energy levels and the structures. I have a small video to show here. You can see this is the p-2. We give the light. You can see these bubbles forming from the reactor. So you can see, so this is hydrogen produced. So we further to do this scanning in TM to see the structure of these polymer parts. If you can see here, we have the polymer DOS2. It has like kind of a hollow structure. The inside seems is nothing or very few things compared with this edge. And we use one pH probe. We put the pH probe inside the cavity of the p-dots. We can monitor the pH inside and outside. So we can see that there's always a pH difference between the inside and outside. There's almost 0.4 difference. It's like in the cell. So the proton can diffuse inside and outside in this case, depending on the photo reaction. So that's why we think this p-dots is really unique. So the structure also holds some like proton channels to benefit the photokinetic reaction. There's one thing I need to mention here, because like I said before, the PD, the residual PD in these polymers, the polymer 1 and the polymer 2 has 0.1% PD, but polymer 3 has 0.5% PD. But polymer 3 does not work at all in this case. So we think the PD may be not the key reactive side in our polymers. But we also did some PD poison experiment, but we did not see obvious decay of the hydrogen production. And we did isotopic experiment to make sure the hydrogen we produced is not from decomposition of the polymers. Yes, so if we use heavy water, we can get the heavy high hydrogen from the polymers. And there's one paper published last year. It's really good, and they confirm like the PD actually is the active side. They remove the PD to almost less than 1 ppm, and actually you can see did not see any hydrogen produced. But I think this is really solid evidence to see the PD is one of the active sites. So if you think about here, if you check the caption here, they did not use the p-dots. They just mixed the PFBDT in the diethylamine and water. So that problem, we are thinking, okay, if we need to think about it in the p-dot structure. The p-dot structure is really unique. It has proton channel. If the organic part is also the reactive side, if you use DEA, actually you shift the proton reduction potential to the negative position. Actually, then you lower the driving force from the organic part to the proton reduction reaction. But the PPD, it has like almost 0.2 over potential to reduce proton to the hydrogen. So we need to think further to verify with p-dots and the low pH. And we also try to remove the PD in our polymers, but we can't remove that until the 1 ppm. But if you see, we can remove almost from 1,000 ppm to 250 ppm. And we did not see significant hydrogen production between these samples. And if we assume all of the hydrogen produced is from the PD, then you can get like a per molar PD how much hydrogen can produce. But that surprisingly, you can see if you have the lower PD, actually it seems like PD is more efficient. But I would like to say is PD could be one of the reactive side, but not only one. Why I would like to say that, if you check the electrokinetic experiment, we use the PFBT P dots. So if you have the PD and the catalyst, PD has over potential for the proton reduction 0.2 volt. So here I versus normal hydrogen electrode is not IIG. So if you think about the pH 4.5, so the proton reduction thermodynamic potential is 0.24. If you plus 2, it should be around minus 0.5. If you have the PD and the catalyst, should see the kinetic peak here, but we cannot see that. We only see the kinetic peak from the polymer dots. And with the P dots and without P dots, we can see the hydrogen produced from the electrokinetic experiment. So we need to think about here, so the P dot structure is unique and it is beneficial for the hydrogen evolution. And benzyl thiodiazole is the catalytic side, or is one of the catalytic sides, or is just work as an assistant side to the PD. So that's some questions we are solving now. So now I come to conclude my talk. So I would like to point out that P dots are really good for the catalyst for proton reduction, even you don't add any extra co-catalyst. And also the P dots can hold the mesoporous structure, which benefits the proton diffusion and the catalytic reaction. Here, the last point I want to stress, that is the thiodiazole unit could be one of the reactive sites in these P dots. So with this, I would like to thank my coworkers. So this P dots project now I'm talking about mainly from Dr. Li Wang and Paula's party and Dr. Ajie Liu and also PhD student Martin Axelson. And also I would like to thank the foundation for the generous financial support, particularly for the Wallenberg Academic Fellow, and their support is the Polymer Dots CAD project. Thanks for your attention.
Thank you, Professor Tian. We finally made it through the presentation. And,
yes, finally.
Yes, and we are going to conclude our workshop for the day. Please note that tomorrow also we have a second part of the workshop, which is 3 p.m. Eastern European time, which is 2 p.m. Central European time. Please log on and you can check it live at the same links. And tomorrow there are some exciting presentations, so please stay tuned. And I must acknowledge the European Commission who funded the project and also this workshop. So the project is funded by the European Commission under the grant agreement ID 828838. Thank you so much again for attending the workshop, and please feel free to comment and ask your questions online at the link and the video that is recorded and will be available, and accordingly we will consult the presenters, the experts, and they will get back to you with their answers. Thank you again. Take care, everyone, and we hope for the best in the coming days and the months for ourselves, for our friends, and our loving families. Thank you so much. Bye from the studio. Indranil Sen here. Thank you.